Databases. We have RDS and DynamoDB. These are our main two types of database managed services, relational database service and DynamoDB, which is our NoSQL store. I'm going to explain what that means in a second. We obviously do have other types of databases, such as in-memory database like Elasticache and column storage like Redshift, but I just want to focus on these two for now. When you're considering what type of data storage to use, there is no one-size-fits-all. You're going to need to look at various aspects of your data, what format it is in, how big are your items that you're going to add to your database, how frequently you're going to access it, how long you're going to keep that data. These kind of things are obviously going to be considerations when deciding which type of database to use. So if we separate the databases into two main factions, we have SQL, transactional relational type databases, and then we have NoSQL, which is your little more unstructured data. And these are the two types. So if you're familiar with traditional databases, and some of you may be already, this is what it looks like, where you have a table with rows and columns, and what you tend to do is you tend to have multiple tables and they'll join, such as you've got like Joe Wilson here who's authored a book. You might have another table over here that says orders for Joe Wilson, the people who have ordered his book, that kind of thing. And you would join the two together and you'd have very structured data, and that's what it's really referring to when you talk about schema. We have a fixed schema where everything has its place and you have all these relations in place. You don't really get that with NoSQL. In NoSQL it's a little more like this, where you have an object and you can keep adding and removing these fields as and when you need and adjusting them without having to change the schema. So it's a dynamic schema. You may start off with an application that just collects the ISBN and the title. Later on you decide to add an author. Later on in your application you decide to add a format. Later on you decide to add price and all these other things. And having a dynamic schema gives you the flexibility to do that, because what you're really doing is you're creating an object and just literally tipping it into NoSQL. Structured databases don't work like that. They need to have this fixed schema. Okay. One of the main considerations when thinking about SQL and NoSQL is the scalability. If you have a SQL database, this is a SQL database here. Maybe we've got a replica slave here. If you want to scale this up, you're going to need a bigger box. So what you do is you replace that with a bigger machine. That's vertically scaling. That may encounter some downtime when you're scaling up your machine. NoSQL works on a series of little nodes, and if you need to scale out, you just add more nodes. Yeah, and this is horizontal scaling versus vertical scaling. Horizontal scaling usually better. So let's talk a little more about RDS. In a lot of ways it's like an EC2 instance that you can cost effectively scale the capacity up and down. You just get bigger machines if you need more space. The main real advantage of using RDS as a managed service versus launching an EC2 instance and loading, say, MySQL on it yourself is that we can handle all the time-consuming managerial aspects. Your typical database admin, things like backing stuff up regularly, patching software, these kind of things. The other advantage of using RDS, other than the fact that we can manage most of the grunt work, is that it's available in all different flavors of database, or many of them at least, such as MySQL, MariaDB, Microsoft SQL Server, Oracle, and Postgres, and even our own Amazon Aurora. One of the other things that's not really mentioned on this slide is that if you have an existing traditional database on-prem and you're trying to get that into the cloud, we have database migration service that allows you to do that, and you can even switch from one type of database to another. We have schema conversion tools and all these other tools to make your life a little bit easier. But fundamentally the idea of RDS is it's a managed database system where we do all the grunt work, and if you're scaling your servers with vertical scaling, we can handle minimizing that downtime. We can make sure it fails over if one machine fails. We can fail over that to another availability zone, promote that to the master, and we can do all these things that you as a database admin would normally have to do on a day-to-day basis. We handle that for you as a managed service. So it's simple, fast to deploy, and use pretty much any of these databases you see here. Secure, cost effective, It's very fast, okay, and it's simple and relatively fast to scale. As far as those backups that I mentioned, now of course you can go and do manual backups whenever you like. You can just do a snapshot and store them into S3, more on S3 later. But the automatic backups are something that happen anyway, because you're using RDS. Will automatically back your database, because that's something you're going to want to do, isn't it? There is also an option to do cross-region snapshots, which is great if you're concerned about disaster recovery. You might want to have a backup of your database the other side of the world. And it can be used as a starting point to migrate your data from one region to another. So we have an ability to do that with what we call cross-region snapshots. So what about security? When you're running your database instance, your RDS instance, you do that inside your VPC. This is not one of those regional services like S3 or Dynamo, which we'll get into a little bit later, which sit outside your VPC. These are actually inside. So think of them as EC2 instances that reside within your subnets that you've created in your network. And as such, you're going to use security groups to determine what entities can come in and out in terms of access, in terms of sending data back and forth. But also you would set up IAM policies, and again we're going to talk about IAM a little later on, and that's going to determine who specifically can have access to your RDS instances. When you create these RDS instances, you can choose to encrypt them, and by encrypting them it means that when we take these regular snapshots, they're automatically going to be encrypted for you. If you want to use a particular style of database's encryption methodology, you can do that, such as Oracle DB and Microsoft SQL Server. You can use TDE if that's what you want to do. We don't restrict you from all of the cool stuff that you have with your database just because it's a managed service. We're just trying to alleviate grunt work for you. You still can go in and do these things specific to your flavor of database. So you can use your own security features of the engine that you're choosing. And also we have SSL as well. Okay, so that's security. Simple application architecture. Here you have a load balancer, and a load balancer is probably the easiest concept in the world. Guess what it does? It balances the load across your machine. So if you have a couple of EC2 instances here and you have traffic coming in, what we can do is we can send traffic to healthy machines. If, for example, this machine is not healthy, for whatever reason, no problem, the load balancer can send all the traffic to this machine. And you tend to put these into different availability zones. So if this set of machines got hit with a meteorite, all the traffic can go here. That's the idea of a load balancer. It's a very, very simple concept. And generally you would be putting this in a public subnet, and you'd have all these hidden away in the private subnet, and only have them accessible via the security groups from the load balancer itself. Now, once this traffic is at your application servers, they're going to need to communicate with a database. Notice the way they all communicate with this master database here. And of course we're going to be doing snapshots to S3, so we can durably retain any snapshots. If this machine went down, we could recover a snapshot from the last point in time snapshot. But there's a challenge with this. We have a single point of failure here. Look at this. What happens if this machine breaks? And machines, as we know, do fail. So in that scenario, your users are out of luck because your application database is down. So how can we get around that? We can simply use more than one AZ. By having multi-AZ RDS deployment, what we're really doing is we're taking a synchronously replicated version of your database into another AZ. Right? So we have one master database which we interact with, and then we synchronously replicate over to another availability zone. And the good thing about this is if the main zone goes down, the main availability zone, for whatever reason, we can promote the slave in the other availability zone to become the new master, and therefore you're minimizing your downtime. And then we can repair the other machine and so forth. And all of this stuff can happen automatically. The downside, of course, with RDS is that you've got two machines, right? So it costs you a little more. But it's definitely worth doing because it's going to give you a resilient, more durable architecture compared to the last one. So if this machine goes down, not a problem, we can promote this one. You get the idea. Let's have a look at DynamoDB. With this you can store any amount of data, there's no limit to that. You do have capacity on each item that you add, but ultimately you can have as many of those as you like. It's very fast because we use solid state hard drives on this. It's going to give you predictable, fast performance, and it's very easy to provision. I'll talk a little bit later on how you actually provision the size of your DynamoDB table, but it is fully managed and it's a NoSQL database service, so it scales horizontally. Let's look at a use case here. This is a company called AdRoll, and they used AWS to grow by 15,000% in a year. They needed a high-performance flexible platform to swiftly synchronize data for a worldwide audience. They're doing 50 terabytes of data a day, 50 billion impressions, stores petabytes of data, and it's had worldwide deployment, allowing them to minimize their latency. As they say here, I love this quote, "We spend more on snacks than we do on DynamoDB." And that's the advantage of Dynamo. It scales to massive heights, but it is also extremely cost effective, especially for a small startup that is just experimenting with DynamoDB. You're only going to pay for what you use. That's very different than RDS. With RDS, when you buy a box, you're paying for that box whether or not you use any data on it or not, and that costs money. With DynamoDB, you're simply paying for the amount of data that's stored in there, and ultimately the capacity that you allow, such as how many reads and writes you want to allow for your application. So obviously that's going to be a lot cheaper than using RDS in many cases. That's what it looks like. We talked before about load balancer. Your application comes in here. Your users hit the load balancer. They go to EC2s. EC2s hit DynamoDB, and this is going to be a regional service. So all of those, regardless of which AZ they're in, can reach DynamoDB, and that can fetch data and return it back to your users. So how does a data model differ from, say, RDS? Well, with RDS, you have tables that join, you have rows, you have columns. They have the same thing in Dynamo, they just name things a little differently. Instead of columns, they call them attributes. Instead of rows, they call them items. Luckily, they still call things tables. Okay. And so, if you were to have a dynamic schema like this, you could have one object which just has the artist, song title and album, and then another object later on that includes the year and genre. So what you have is these gaps, and in NoSQL that works just fine. That works really well, and it means that your schema is very flexible. So that's really the main difference in terms of the data model, and it's extremely fast to read and write to that. You do need to provide a partition key, and if you're familiar with the traditional SQL world, you might know of a primary key. We have a similar thing with a partition key. This partition key for your table is going to need to be unique. So maybe you have, like, I know it says artist here, but you might have customer ID, it says 1, 2, 3, and 4, that kind of thing. And that would need to be unique so that then you can search on that partition key and extract one or more of the attributes back in the query. That's the way that works. When I first saw Dynamo, I thought, I don't see how this is that good, right? That was my first reaction, because you can only search on the partition key. So you can't search for all of those items on a specific year or a specific genre. You can only search on the primary key or the partition key. Well, luckily, there is more to it than that. You can create what we call indices, and they lay on top of your traditional table and allow you to essentially create secondary partition keys and be able to search on year or search on genre. So you add that to your additional table. They're called indices. I'll get onto that in a little bit. This sort key here is where you can't create uniqueness on the partition key. So in some cases like this, where we have an artist, you may have bands that have the same name, but they have different song titles, and the combination of the band name and the song title, that is unique. So you can create uniqueness by having what we consider a compound key, where you have a partition key and a sort key together to create that uniqueness. Okay, well, then that's pretty straightforward, right? When we do developing courses on AWS, we spend quite a lot of time talking about global secondary indexes, or GSIs, local secondary indices, partitions, how to provision throughput and all these things. I'm purposefully going to keep this relatively high level because I don't want to get into the weeds on this. But the idea of a global secondary index is nothing more than looking at your original table and specifying a new search key. So this table here, you cannot search on genre, you can only search on artist. If you create a GSI, you can then search on genre. And you notice if this had, maybe this had 1 million items in it, right? And your index could have maybe 100,000 items, only the ones that had a genre listed, like these ones, and the rest aren't even added to the index. This means you have nicer, shorter, succinct indices compared to your tables, and these are much better to search through. So when you find that you want to search on particular areas, you create indices for those. I think at this level, on a Tech Essentials, that's as deep as I really want to go. We do have LSIs. Feel free to ask your questions in the chat window, but I'm just going to move past that because it does get a little bit more complex. And again, I'm only going to touch on a high level here with the provision throughput. I'm not going to go into calculations. But when you're defining how big your DynamoDB system is going to be, you're really defining how many reads and writes you're going to allow. So each item that you have, or each row in DynamoDB, can be a maximum of 400k in size. You size your table based on how many reads and writes you need, or what we call RCUs and WCUs. So if you had, maybe you had an item and it's 10k in size, and you wanted to write that every second, you're going to need 10 WCUs to be able to write that item every second. You get the idea. The read capacity is based on a strongly consistent read, and I'll get into the difference between these two in a second. Let's just look at the strongly consistent read first. If you had an item and it was 4k in size and you wanted to read that every single second, you'd need 1 read capacity units. If you had a read requirement of maybe an item that's 6k and you wanted to read that every second, you would need 2 read capacity units to over provision. Because if you only had 1 read capacity unit, which allows you 4k, and your item is 6, is not going to have enough capacity to read it. You would need to provide or provision 2 RCUs to have 1 strongly consistent read on a 6k item. Okay, as you can see, this can get quite complex if we start getting into the weeds on this. I'm not going to. I will, though, discuss this concept: strongly consistent and eventually consistent reads. When you make queries to DynamoDB, it's done through a cluster of nodes. So you have all these nodes, right? When you have an item, maybe let's choose a color. Let's say an item in here is green, and that is populated across all the nodes in that region. And then later on you say, I'm going to change this color from green to blue. Now, as that blue is propagating through all the nodes across all of the buildings in the region, if a query comes in and queries this one, it's going to be different than the answer that it gets from here, isn't it? If a query comes here, they think it's green. If a query comes in here, they think it's blue. And this is the problem of a distributed system. You have eventual consistency. And as such, if you just do the standard reads, it's going to grab the first node it can and return the value. And in some cases, that might not be okay, such as banking transactions, where you need to have that strong consistent read. So what would happen if you do a strongly consistent read? This will wait here and collect all the information off all the nodes and evaluate this is the latest one and return blue, not green. That's obviously more expensive because it has to look through the other nodes. So strongly consistent read is more expensive, or twice as expensive as the default eventually consistent read. You specify whether it's strongly consistent or eventually consistent when you make the query. Why do we have both? Well, in some cases you need that strong consistency, but in most cases we don't think you do. For example, if you're updating a status, maybe on a social media network, and you're changing a status and that's propagating through, if somebody the other side of the world sees the old status for maybe a second, it doesn't break your application, doesn't really matter that much, but we understand in some cases it does. And so you can pay a little premium and have the strongly consistent read if you prefer when you make that query. Alright, that's all I'm really going to go into in terms of depth on that, if that's okay. So finally, with some database considerations, if you need really fast reads and writes and you want to have really nice scalability and low cost, and you pay for what you use, DynamoDB is probably the way to go. I would suggest if you start a new project, start with Dynamo, and if you find that you need to have relations and transactions and that kind of stuff, look at RDS. Okay, because you can have different types of database. You've got multi-AZ for that failover. We will minimize the downtime when you're doing the vertical scaling, or if there is a failure with a master node, we will replicate, we will promote the slave, we will do all these things because it's a managed service. But these are the two choices you've got. The final option, if neither of these two choices or two options for managed services, none of them suit your needs, of course you can go down to the metal. You can go to an EC2 instance and install MySQL or MongoDB or anything you like on there, and that gives you complete control and complete power of the system. However, I would say you've got a lot of grunt work involved in that, and this just makes your life so much easier. Okay, so I would look at managed services because we're following best practices, best security practices when we provide these managed services to you. Okay. Amazon S3, I guess this is one of the most common products. It's usually one of the first places people go to when they start working with AWS. It's usually a toe in the water approach. Many companies will maybe just store a database backup or some item of value into S3 just to test the cloud, and then over time they start moving on to other services. We see this a lot. So S3, all it is a simple web service interface to store and retrieve any amount of data, which is a pretty bold statement. I mean, there are some restrictions on individual items you put into S3. There are some size limits, which we'll get onto later. But the idea, you can have as many of those items as you like. It's a huge data lake where you can store almost anything. And it can be accessed anytime from anywhere on the web, providing you've enabled access, because as you know, everything is locked down by default, and it is up to you to expose the objects you want exposed, and everything else remains locked down. It's going to be highly secure, durable, meaning once you put something in S3, it's replicated across multiple availability zones because it's a regional service. So it's very durable. The chance of losing objects almost minimal, and it's very scalable, which means you can throw any amount of data at this thing. So some use cases. I mentioned before that companies like to maybe store database backups in there or store logs. It's also good for static website hosting if you want to just store a typical website, index HTML, JavaScript files, CSS files, fonts, this kind of stuff. It's wonderful for that because you don't have to provision EC2 instances and load Apache on it. You can just host a website straight out of S3. A static website, I don't mean a dynamic one. Disaster recovery, this is another aspect. People would have a copy, or companies would have a copy of their data, perhaps stored even in a different region, and then they can replicate from that data source and handle things like disaster recovery. Backup and archiving, that's probably the most common one though. Also, big data analytics, we're seeing much more of this. A lot of companies now are throwing data into S3 in various formats from various sources, and just literally tipping the kitchen sink into S3, and later on looking back at that data and making sense of that data with things like managed Hadoop, such as Amazon EMR or Athena. So let's look at some key concepts. You store data in S3 in what we call buckets. Right? These bucket names that you create in your account aren't unique to your account. This is actually a really important point with S3 and bucket naming, is the bucket names that you create have to be unique across the whole universe. Right? They're globally unique. It's not per account, it's not per region. If you declare a bucket name to be called My Amazing Bucket, nobody else can have a bucket called My Amazing Bucket anywhere in the world. Okay? So they're globally unique. Think a little more like domain names. There are some naming conventions on your bucket names. You can only have a certain amount of characters. You don't use lowercase letters, numbers and hyphens. Avoid using the period character. You can use a period character, but I would avoid using it. It causes some problems down the line with SSL and a few other things. But just tend to avoid it, although you can use that. I'll get onto versioning in a second. I'll come back to that one. And buckets are associated with regions, and regions, they vary in terms of their cost. And obviously it varies in terms of the latency. If you have users here, it makes sense to get the information from here instead of going all the way over here, right? So you want to choose your bucket locations because it's a regional service. You want to choose that based upon, where your customers are, where your data is being moved around. Because data moving within a region is going to be free, but once you start moving data outside a region, that's when it starts to rack up costs. Another consideration that's often overlooked is regulatory requirements. If you have a social media network over in one part of the world and you're collecting user data, there may be some regulatory restriction on moving that data outside of the region. So even though Amazon Web Services allow you to do many things like move data around regions, just because you can doesn't mean you should. So there are certain considerations you have to look at, such as regulatory compliance. Okay. So let's look a little more at these objects. What you're looking at in the bottom right here is a version enabled bucket. Meaning when you just throw an item, say collections HTML, it's an HTML page, and you throw that into an S3 bucket that you've created, if you then overwrite that, it will replace the old object. However, if you choose to, and you would have to proactively do this, if you choose to, you can set up versioning on that bucket, which means when you overwrite it, it doesn't actually overwrite it. What it will do, it will just create the new version on top of it. So you have two full objects, not the difference in the object, two full standalone objects on top of each other. This is useful because if at any one point in time you decide to delete an item and it happened accidentally, if you had a non-version bucket, your item's gone. If you have a version bucket, what happens is it creates a delete marker. I should probably change ink for this. It creates another one on top of here, which is a delete marker. Saying marker. And when a request comes in, it sees the delete marker and goes, oh, I'm going to return a 404 not found. This is not there. How do you restore the object? You can guess. Delete the delete marker, and then it sees the object below it. It also means you can identify items by their version ID as well, so you can get specific versions of your object back. That's what versioning allows you to do. That is something you proactively activate. By default, they're not version enabled. Okay, normally when you overwrite an item, it's overwrite it. Normally when you delete it, it's deleted. Each object that you upload also has some associated metadata. Metadata can be things like how long it's going to stay in cache in terms of your content headers, other bits and pieces such as tags, all of these things. Again, I'm going to refer you to the docs. You can add metadata surrounding the objects when you upload your object or after you've uploaded it. So these are the URLs that are created with S3 objects, structured as so. Defines S3, the region, our domain name, your bucket name, and then your object name. So they can get a URL that if someone goes to that URL, they can get hold of your object. Now, of course, you have to enable that. You have to either make it public or make it available to them with either a pre-signed URL, or it has to be someone in your organization with the appropriate role, or a bucket policy that we have on there. But once they have access, they can access it via that URL. And in many cases, if you're hosting, say, a website, you want to use a different URL. You would structure it more like this, where you have your bucket name at the beginning, then S3, our domain name, and then your object key, as it says here. This way, you can configure your own domain name to point to said URL. And that way you can have a website with all your information in here and host a full static website on your own domain. Let's look at put operations. This is nothing more than uploading objects or even copying objects over to from one bucket to another. When you upload an object, because there is no real size limit within reason, I mean, you have like a 5 terabyte limit, I mean, that's huge. But generally there's no limit to the size. You just throw any kind of object in there. But once it starts getting over 5 gigs, you want to start breaking it down into multi-part uploads. We actually recommend using multi-part uploads and breaking it into chunks even at a very, very small level. So we would go as far as to say, don't wait till the item is a reasonable size like 5 gigs before breaking up. Actually break up your object at the 100 megabyte size and start uploading it in chunks. This way you can resume an upload. There'd be nothing worse than uploading a 5 gig file or a 5 terabyte file and getting to 4.9 and then the connection dies and you have to start all over again. So being able to use multi-part upload is obviously going to be advantageous for you. Great for moving objects across S3. You can also update your metadata. You can do that when you load the original object, and you can also do it afterwards as well. Copy operations, just create a copy of an object, move it from one bucket to another or even to the same bucket. Just essentially doing a rename and then deleting the old one. So we have all these options for operations on an object. Oh, and by the way, just so you know I talked about chunking this up and creating a multi-part upload. The APIs that you use when you're programming with S3, or even if you're using the console, they hide that from you. That's just what's going on under the hood. From your perspective, you just put in an object into S3, job done. It takes care of this for you, it handles that for you, okay? It's transparent. You can control it at a granular level if you're really involved in that stuff and you want to. We have an ability to do that with SDKs, but generally it's hidden from you. Same goes for gets. You can get the complete object, or you can, if you choose to, you can get a range of bytes back. You don't have to get the whole object, you can get it piecemeal. So these are typical operations. You can also list keys. This is not the most efficient thing in the world to do as far as listing objects, because S3 is a key value store. It's not like a database where it does very fast reads in terms of looking and listing through items, but you can list items inside a bucket, but it's not done on folders. What do I mean by that? It looks like it's a folder, doesn't it? If you look at this, these look like folders. They're not actually folders. These are actually just key values for the whole key. If you were to replace this with underscores instead of forward slashes, you'd get an idea of what it is. It is just a simple key value flat file system. We don't have folders, we don't have a typical structure like that. It's a key and a value. Nothing more complex than that. Which means if you want to search on, say, scores, you're searching on what we call a prefix. You're not searching on a score folder, you're searching on the prefix 2014/SCORE/. Okay? It's probably not that relevant to you to know that. I just think it's important contextually to be aware of it, that it is a flat file system with key value pairs, not a folder structure. Okay? I've already covered this. This was what I mentioned before, your traditional object here, and then when you have version enabled, if you try to delete an item, it creates a delete marker. We've already discussed that, okay? Something else you can do. If you store something in S3 and then decide that you don't need constant access to it, you can put it on ice. You can take that object and put it in a service called Glacier, and you can automate these rules, of course, but if you move something into Glacier, it means it's going to take a while, maybe a couple of hours, to get that object back if you need it. Why would you do that if it takes so long to get the item back? The reason you do it is because it's dirt cheap. If you can put something from S3 into Glacier, the storage costs in Glacier are a fraction of the cost of S3. Downside, of course, if you need to thaw that object back out and restore it from Glacier to S3 so you can have access to it, it takes a couple hours. Now, of course, there are mechanisms where you can accelerate that by paying a premium and these kind of things, but generally you think of the concept as if you take something from S3 and put it in Glacier, it's going to take you a while to get it back, but it's cheap. So I've been talking about IAM briefly throughout. I've mentioned it's a way to lock down which entities can communicate with which other entities, such as users accessing a resource like Dynamo, or a group of users accessing S3, or the public accessing a particular resource. All of this concept of authentication and authorization is handled within that service I've been mentioning called IAM, Identity and Access Management. This is a way to centralize and manage your users and their permissions within AWS. And using IAM, you can create users, you can put users in groups, and you can apply policies, well, so essentially permissions, to those sets of users, whether they're individual users or groups. And in some cases you might want to even use roles, which we'll talk about in a little bit, ultimately providing entities such as EC2 instances or Lambda functions, which we'll also talk about later, to access other resources, because they're not users, aren't they? They're EC2 instances, they're Lambdas, they're not real users, and as such we apply something called roles. More on that a little later. So you define your permissions to control which access patterns you wish to set up, and if you want to, you can also integrate IAM directly with Microsoft Active Directory. So if you have your own on-premises system which has authentication, you can tie that in with IAM so you don't have to create loads of new IAM users. So let's get started with IAM. User account provides one login and its own specified permissions, and a group allows you to apply specified permissions to a group of users, such as a dev group or a database users group. And roles allow you to apply permissions to entities such as EC2 instances or Lambda functions. You can even use roles to allow users to access certain resources as well if you want to. When you first create your AWS account, you'll be set up with a username and a password. So a login and a password that you see here. My recommendation, don't ever operate from that root account. What you should be doing is you should go into that root account, create an IAM user that has admin rights, in this case like Maria, log out of your root account and log back in as Maria. And from that point on you can then start administrating your system. And the animation is showing you creating users, creating groups, as you can see, developers, analysts. Okay, in that case they're assuming a role to do some MapReduce jobs or work on a dev app. I think you get the idea, right? So as far as credentials go, you can use your traditional username and password that you get set up when you first create an account. I wouldn't do that. I would create an IAM user that has its own username and password and use those to access the console. If you choose to, you can use the command line tools or the software development kits or the query APIs, and as such when you're using those you don't use a username and password. You use a specified access key and a secret key to uniquely identify you and sign your requests. We'd cover more on this if we were doing, say, a developing course. And of course, multi-factor authentication is extremely useful, meaning that my machine that I'm on right now, if I lost my machine and someone got hold of it, they still won't be able to access my AWS account, because even if they happen to know my username and password, it would prompt them for an additional key which I have on a Gemlock token or an MFA application I have on my phone, and that way it prevents someone stealing your account, and it just creates this two-factor authentication. That's what MFA stands for, multi-factor authentication. I'd recommend setting that up on your root account as well. Again, I really want to avoid going into any depth on this because this is more of a developing concept, but if you are programmatically interacting with AWS, you're not going in pressing buttons in the console, you're actually programming it with, say, Node.js or Java or some other language, you would need your access key and secret access key to be able to make those requests. That's all this is. So use credential files, use temporary credentials when needed. This refers to roles, meaning that instead of hard coding your credentials in your source code and deploying it to a machine, the best thing to do is to create a role on a machine, such as an EC2 instance, and when that EC2 instance needs to communicate with other resources, say S3 or Dynamo, before it makes a request to it, it will go and get temporary credentials and use those. That's just a safer mechanism. It means you don't have to deal with rotation in your credentials, you're not hard coding your credentials in your code, just generally a better way, and that's called roles. Let's talk a little more about these policies. They're nothing more than statements describing what you can and cannot do and what you have access to, what you don't have access to. You don't really use this for operating system or application level permissions. If you're building an app that people use and you had 1 million users, you won't create an IAM user for each of those. IAM policies aren't designed for that kind of stuff. You should be using them for people in your organization or even third parties that want to interact with your AWS account. Maybe you have a third party that wants to read something from one of your queues in your dev environment. You can do that using roles and policies. But always, always, always provide least privilege. If you're allowing anyone access to your resources, make sure they can only access the resources you want them to access and lock everything else down. So how do you identify individual resources you want to lock down? We have something called Amazon resource names for that. And these are just unique identifiers. So if you need to uniquely identify a DynamoDB table in a particular region, in a particular account, you can do that with this ARN. This is going to be unique to that resource. The same for S3. You've got one here specifying a bucket. You might be thinking, well, wait a minute, what are these double and triple colon things? They're gaps. When I first saw this, I was confused by that, and I realized all they are gaps. So this would be your region, and this would be your account number. Why are they gaps? Why are they left out? And the reason is you don't need to specify a region or an account number to uniquely identify this end bucket, because the bucket name is globally unique anyway. Yeah, that's why you're seeing those gaps there. So it's a shorthand way of writing that. Once you know those ARNs, or Amazon Resource Names, you can uniquely identify things in your policies in order to determine who has access to them and who does not. So here's an example of an IAM policy. It's what it looks like. It's just a JSON document, just a text file. And what you're saying here is you're allowing anyone to access, whoever holds this policy is allowed to interact with EC2, specifically in this region, specifically in this account, specifically this instance, and can do pretty much what it wants to with EC2, provided both of those conditions are true. So when you run an IAM policy, it's smart enough to know a few things. It knows the tag that's on the EC2 instance that you're trying to interact with, and it can check whether it's labeled as test or not. It also is smart enough to know the current time and can check it against a timestamp you set. So here, as long as a request occurs before the beginning of the year 2016 and the tag had department equals test, then they'd be able to access it. If neither of those or either of those were false, they would not. Okay, so that's how a condition works. So IAM is pretty smart that it can do conditions on resources. So how do the permissions work? Well, we have a couple of different permission types. We can have user-based permissions, such as Bob, Larry, or a group here. This would be a group of managers, yeah? Or you can have the resource-based policy. Generally have a combination of all of them. And with these permissions, there is no structured hierarchy. It's not as if you add a new policy and that overrides the previous ones. The way I like to visualize policies and the way the permissions work within IAM is I think of three pieces of paper on a desk. The first one is the user-based policy, such as Bob's user policy that he carries around with him. You have the group policy that Bob is part of, and then you have the end resource policy, the resource policy based on maybe S3, for example, or Dynamo. And what you need to do is you need to take each individual policy and put them down flat against each other and scan through all of those three policies. If anywhere on any of these policies there is a deny, meaning that either the resource says Bob is not allowed access, or the group is not allowed access, or the user itself is specified no access, they do not have access. So the first thing you do is you check for a deny, and if there's a deny in any of these, that's the end of the story, they do not have access. Say, for example, there is no deny specified across any of these three policies, not on the user, not on the group, not on the resource. Does it mean they have access? And the answer is no. They still have to specify an explicit allow on one of these. It doesn't have to be all of them, but as long as there is an explicit allow on one or more of these, and there is no previous explicit deny, only then do they have access. Otherwise, can't get in. Okay? So it's not a hierarchy. It's not a which one comes after another. It doesn't work like that. They're equal. Okay? User, group, resource, you look at them all and you analyze from there. So here's a user-based policy on the left and a resource-based policy on the right. What's interesting about the user-based policy is this part here. You see this dollar symbol, AWS username? Remember I said IAM policies are pretty smart, and knows things like current time, that kind of stuff, knows what tags are on an instance, that kind of thing. It also knows the user that's actually attempting to use the policy. And as such, you could have a resource here specifying a specific username to access their own login profile. This should probably be called a group-based policy. This would make more sense to apply to a group, because if you had 500 people in a group, you could apply this single policy, and the IAM policy will be smart enough to know who's making the request and only give them permission or access to their own stuff. That means you won't need to provide policies on users. You can just add one policy to the group and associate people to the group. Easy, right? That's what resource-based policy looks like on the right. This is saying an S3 based policy. Whoever is trying to access this bucket from this account can only access these individual resources. Okay, so there are your two types, user-based, resource-based. This is kind of useful. Remember I said before, once you have an explicit deny, that's the end of the story. It doesn't matter if you have explicit allows, they're irrelevant. If there's a deny, that's the end of it. So what you can do is you can say, I would like to deny everyone access to putting objects in S3, specifically this bucket, unless it's encrypted. This is great for compliance. It means you can't accidentally throw something in S3 and it's not encrypted. These are the useful things policies can do. So how do you create those policies? You know that JSON document I showed you before, that's a policy. How do you create that? Well, you can go into a text editor and edit a policy, of course. Or you can use the tools available to you in the console. And in the console you have a range of managed policies with essentially template policies, such as code commit power users, S3 read-only user, that kind of stuff. You can go in there and choose a managed policy and essentially pick a policy off the shelf that's abiding by general best practices. Again, you should always be aware though of providing the least privilege at all times. Now if one of these managed policy templates that you choose in the console doesn't really fit your needs, well, you've got a couple of options. You can either take that as a template, modify it and then save that back as a customer managed policy and use that. I don't recommend that. What I would do is I would keep the managed policy in place and add an amendment. Just add an additional smaller inline policy to add on to the existing one you've got to lock it down a little more. Such as you might have a managed policy for a code commit power user, and then later on you add an inline policy to say, that policy is good, but I only want them accessing these specific repos. And you can lock it down a little more with an inline policy. Okay. If we're on a dev course, I'd show you a demo of that. We don't really have time, unfortunately, for that. So working with these policies, you can obviously use a text editor for that. Use a policy templates that I just talked about. But also you can use a policy generator. So you can use a series of drop-down menus in the IAM console to create a policy, and then out the other end comes a beautiful JSON document describing your policy, which you can edit. You can use the SDKs or CloudFormation, which we don't really cover in this course. This is a matter of scripting your infrastructure as text. You can use SDKs, or you can use Visual Studio or Eclipse. There are ways you can interact with IAM. This slide here, and I always say this when I do this course, is probably the most important slide of the whole course. Right? Because if you're going to pay attention at any point during this course, now is the time, because this is very, very important to understand. And most people kind of nod away and think, yeah, I get this, but generally they don't always get it fully. So here's the important thing I'm just going to go through. We're going to start with the assumption that everything is denied. In other words, when you create an IAM user, they can't do a thing. You then have to give them access either with a user-based policy, a group-based policy, or a resource-based policy. So you're going to evaluate all of those policies, and if you see an explicit deny, that's the end of the story. Nothing they can do. It doesn't matter if you add stuff on later, doesn't matter. They can't get in. If there's no explicit deny, still can't get in. Right? It's pretty cool. They would have to be explicitly allowed as well, and that's the only way they can get in. So if something is explicitly denied, it can never be allowed. There is no way to override it. And that's given in this example. So what you're seeing on the top part here is you're allowing whoever holds this policy to access Dynamo and S3, specifically that Dynamo table, specifically that bucket and the contents of said bucket. But there is also a section here denying everything outside of it. And you might be thinking, well, why do I need that? Because didn't Rick just say that when you have a policy in place like this, if you haven't explicitly allowed it, they're denied? Right? So if everything's denied by default, why on earth would you bother writing any of this stuff down here? Because it's not as though they can access bucket name 2, because they're not explicitly allowed. And the reason is, you might want to really lock down a policy, or really lock down a user. And this means that if you add the deny section below your policy, later on if that person joins a particular group that has access to bucket name number 2, they still do not have access because you've explicitly denied them. Yes, in the real world that's probably awkward, that's probably unrealistic, because if you're joining, say, Bob to a database administrator group, you're going to want Bob accessing databases, so you're probably going to want them to have the permissions of the group. But hypothetically, if you wanted to really lock down a particular policy, you can do that with an explicit deny, because no matter what they have later on, they can never get in because of this. Okay? This gives users access to a specific Dynamo table and S3 buckets, and the explicit deny ensures that users cannot use those actions or resources other than those tables and those buckets, no matter what. Okay? That's where you do something like this. You have a blanket policy that denies absolutely everyone from doing anything. unless they happen to be in a range of IP addresses that they can make requests from, such as building 1 or building 2 in your organization, or their home address if they had a hard-coded static IP, that kind of thing. Okay, so if a user in your organization leaves a building, goes to a Starbucks over the road, they can't interact with S3 because explicit deny is blocking it, even if they're the CTO. Yeah, you get the idea. One final thing on IAM, trust policies. Every time you create a policy, user, resource, it doesn't really matter. Okay, you need to determine whether the person that's going to use that policy is allowed to do it, is allowed to use that policy. And this is what you're seeing here. You're saying that Joe is allowed to use the policy below it. So this is a blanket policy saying anyone who has this policy is allowed to access S3, right? The only person that's allowed to assume this policy is going to be Joe. This is very useful for scenarios whereby you have an EC2 instance that can be operated by Bob, and Bob can do what he likes with the EC2, but Bob is specifically or explicitly denied from access to Dynamo. So how does Bob get creative? How does Bob get his hands on Dynamo? If he's explicitly denied, there's nothing he can do, right? Or is there? What happens if Bob decides to launch an EC2 instance with a role that can access Dynamo? He just hacks his way into Dynamo, hasn't he? This is why trust policies are important, because it helps you get around that kind of thing. Because you can say, okay, Bob, you can have this policy here that allows you to do stuff with EC2, you're good with that. But you're only allowed to pass in a specific role to that EC2 instance that can do things we're letting you do. And you do that with pass role. So when you're launching, say, an EC2 instance or a Lambda function that is going to assume a policy, before the console lets you create the policy, it's going to ask you what type of policy. And really what it's asking you for is a trust policy. You're saying that this is going to be a function designed to be assumed by Lambda functions, or this is designed to be a role assumed by EC2 instances, and you specify that before you write your policy. And that is what we mean by trust policy. Okay. And again, I'd kind of love it if we had more time together and I'd show you this demo because it'd make a lot more sense. It's just, we just physically don't have the time to do it, unfortunately. Finally, I just want to touch on this real quick. You can use the concept of roles and policies to do some really interesting things. Imagine you build an iPhone application. You could let users log in with Google or Facebook or Amazon, get a security token, hit AWS, and get temporary credentials, an access key and a secret key, and use those credentials to access resources. But what you notice about this is really cool, is there's no EC2, there's no API gateway, there's no load balancer here. We're talking about an iPhone app interacting directly with Dynamo, yeah, based on policies. So that really does open up a tin of worms, doesn't it? There's many things you can do with these policies and with roles, and behind the scenes it uses what we call STS, Simple Token Service, to do this stuff. But you can do some very, very interesting applications with this. And again, if we were on a dev course, we'd get into the weeds on that. We don't really have time though. So that's IAM. So we're pretty much at the end of the course. I hope you enjoyed the course, obviously. I hope you got what you needed. I am going to leave you with one final thought though. I've talked about some of the core concepts within AWS. We've covered a lot of things like EC2, VPC, S3, Dynamo, RDS, IAM. We've covered a lot of ground, but I just want to whet your appetite on one concept. We obviously don't have time to go into it, but I just want to whet your appetite on a concept. This Lambda is probably the biggest game changer we've seen in the cloud computing industry. The idea that you can run code in response to events and you only pay for the time the code runs. The beauty of this is you don't have to administer it, you're simply providing your code and it runs in response to an event. We'll manage all the compute resources for you. If you have a website that gets 1 hit a day, 1 hit a month, that's fine. You get 1 million hits a month, not a problem. No auto scaling, no load balancing. You're simply paying for the code when it runs. I urge you to look into Lambda. I see this as being the next big thing. Anyway, I want to leave on that note. Thanks for attending. My name's been Rick Hurst. Thanks for listening.